Welcome to this explainer. Today, we're taking something that usually gives biology students nightmares, metabolic regulation, and decoding it. We are going to take information that often feels completely overwhelming and distill it down into a crystal clear visual logic, basically transforming a massive list of enzymes into a highly organized biological computer network. Let's jump right in. Here's our roadmap for this explainer. First, the logic of regulation. Second, mechanisms of enzyme control. Third, pathway architecture and thermodynamics. Fourth, systems modeling and flux. And finally, adaptation and biological homeostasis. We're going step by step from the micro level of a single chemical spark right up to macro level organism adaptation. Section 1. The logic of regulation. Let's get right into it and establish the fundamental logic that governs biological demand versus output. Okay, look at this. At first glance, this network looks incredibly intimidating, like a subway map drawn by a crazy person. It's a massive web of interconnected pathways, loops, and cycles. But here's the thing. This massive web operates under incredibly strict logical rules that we are about to untangle. It's not random chaos at all. It's a beautifully choreographed system. And that brilliantly illustrates our first insider secret, our first major exam focus, if you will. The primary directive of a cell is to match its metabolic output directly to its biological demand. Notice how the physical scale here perfectly balances the two. The system is designed to prevent energy waste, specifically the burning of ATP. You absolutely cannot afford to build something up and break it down at the exact same time in what we call a futile cycle. Your cells are just too smart for that. Section 2. Mechanisms of enzyme control. Now that we understand the why, let's zoom in on the how and look at the fast and slow mechanisms controlling our individual enzymes. Think of fast regulation like slamming the brakes or hitting the gas on a car that's already cruising on the highway. You're altering pre-existing enzymes in a matter of seconds to minutes. Slow regulation, though, that's like stopping to build a completely new car. It changes the actual amount of enzyme over hours or days through gene transcription. So, major tip here. If you're looking at a test scenario that needs an instant, immediate response, you can automatically eliminate any transcriptional control options. It's just too slow. So how do those fast hit-the-brakes mechanisms actually work? Well, we've got substrate availability, covalent modifications, like slapping a phosphate group on there, and allosteric control. Now, pay super close attention to the allosteric feedback inhibition section here. The exam focus is that feedback inhibition automatically shuts down the entire pathway, not just one isolated step, the whole shebang. And it does it entirely on its own, no external signals required. But it gets even cooler when we look beyond just single proteins. Sequential enzymes actually physically organize themselves into macromolecular condensates. They literally clump together into structured filaments, like a molecular assembly line. This physically coordinates entire pathways and keeps the intermediate molecules from just drifting off into the cellular abyss. Section 3. Pathway architecture and thermodynamics. Let's zoom out a bit more. Let's explore how energy and pathway architecture actually dictate where these control valves go. Imagine you're a plumber. The enzymes driving reactions that are far from equilibrium, where there is a massive, steep drop in free energy, are your highly controllable, heavy-duty valves. They are like a water tower pushing flow through a tight pipe. On the flip side, reactions near equilibrium are basically flat puddles. The water just sloshes back and forth, making them practically impossible to control effectively. So, architecturally speaking, where do you install those essential heavy-duty valves? The optimal spot is the first committed irreversible step right after a metabolic branch point. Look at glucose 6-phosphate here. It's got options: glycolysis, the pentose phosphate pathway, or glycogen synthesis. By placing the regulatory valve immediately after it chooses a path, the system guarantees that resources are locked in and routed to the exact right outcome without wasting any energy. All right, brace yourselves for a massive paradigm shift. This is an exam focus that trips almost everyone up. In a test tube, in vitro, we usually look at equilibrium, right? You add substrate and that amount determines how fast the reaction goes. But inside a living cell, in vivo, it is completely backwards. Pathways operate at a steady state where a constant velocity is maintained, and it's that constant velocity that actually dictates the substrate levels. If it didn't work this way, you'd get massive, lethal metabolic traffic jams. Section 4. Systems modeling and flux. We've got the architecture down, now let's step up to the ultimate macro level. systems biology, and mathematically modeling that flux.
To actually simulate all this steady-state traffic, we use metabolic control analysis, or MCA modeling. And the backbone of MCA? Ordinary differential equations. Now, don't let the math scare you. ODEs are essentially just simple balancing acts of the flux coming in minus the flux going out. A positive sign means you made a metabolite. Negative means you consumed it. It's wonderfully straightforward biological accounting. Now, when you're looking at the metabolic control analysis dashboard, please do not fall for this classic exam trap. You absolutely must differentiate between global system properties and local ones. For example, the flux control coefficient, that's global. It represents a fractional change across the entire pathway's flux. But the elasticity coefficient, completely local. That strictly describes an isolated enzyme's response sitting in a test tube.
So, before we look at our next slide, I have to ask a question to bust a myth that's been drilled into us since high school biology. Is there actually a single, narrow, rate-limiting bottleneck that controls these whole pathways?
Actually, no. The rate-limiting step is basically a myth. The summation theorem mathematically proves that control isn't held by one dictator enzyme. It is distributed across all enzymes in a network, adding up exactly to 1. As you can see mapped out here, perturbing just one enzyme ripples out, altering the steady-state concentrations of all intermediates and affecting literally every other enzyme. Because of end-product feedback, the control is smoothly shared by the whole system.
Section 5. Adaptation and biological homeostasis. Let's pull every single piece of this together in our final section and see how this incredibly distributed control creates perfect organismal harmony.
First up, we really need to nail down what steady state actually means. It is a biological condition where internal variables stay totally constant, even while processes are constantly churning. The key takeaway? Steady state is a highly active, energy-demanding balancing act. It is absolutely not passive equilibrium. Honestly, in biology, passive equilibrium just equals death.
To keep this intense, steady state going, our biological networks lean heavily on these S-shaped sigmoidal curves, like the green line shown here for multimeric allosteric enzymes. Unlike boring linear or hyperbolic responses, these sigmoidal curves act like binary biological switches. They create a sharp activation threshold, which brilliantly filters out low-level background noise. The system only fires when it gets a legit, strong signal. So what happens when that strong signal hits? Well, for a system to achieve what we call perfect adaptation, it has to transiently spike its response, like that sharp peak you see right here, and then drop all the way back down to its exact parameter-independent baseline state, even if the stimulus is still hammering away. If it doesn't adapt and just stays spiked, that constant activation is a one-way ticket to toxicity or unchecked cell proliferation. The actual molecular circuit boards pulling off this perfect adaptation are genius. They use motifs like negative feedback loops and incoherent feed-forward loops, which basically means one single input is simultaneously driving two totally opposing outcomes. But here is the critical exam focus. Both of these circuits completely depend on a built-in time delay. Without a lag in producing the inhibitor, that beautiful transient spike and reset simply cannot happen. And taking one last look at this timing at the protein level, we have state-dependent inactivation. Three-state proteins, like voltage-gated sodium channels, go from closed to open and then to an inactivated state. They are forced to undergo a mandatory refractory period, a recovery phase, before they can physically reset to closed. It is a really elegant way to prevent proteins from getting permanently jammed in the on position, which allows for rapid, controlled, repetitive firing. We've just unpacked the incredibly precise logic of how our cells balance output, route resources, and lock into a steady state. So I want to leave you with something wild to think about. If our entire metabolic harmony relies on these precise, time-delayed resetting circuits, could devastating diseases like cancer simply be what happens when this incredible internal computer network loses that delay and forgets how to turn itself off? Think about that puzzle as you review these concepts, and I will catch you in the next explainer.